All right. Well, thank you for joining this video. And in this series of videos, I want to kind of in detail go over a very fundamental text in plasma processing. It's called Principles of Plasma Discharges and Materials Processing by Michael Lieberman and Allan Lichtenberg. So I have a copy of the text right here, and you can see that it's been gone through quite a bit. You can see that the sections that have been that I've used a lot more over the course of my research have been stained yellow. And for a lot of people, this is considered sort of the Bible of plasma processing. And I think the much like the Bible, when you first get it, it's incredibly dense and doesn't necessarily make a ton of sense, but there's a lot of value in it. And it requires going back to over and over again to kind of develop understanding. And the more time, every time I've gone back to the text and reread sections of it, I have gotten more out of it. So it's my hope in this series to kind of go through each chapter, each paragraph, and provide commentary of my own. And it's just as much a learning process for me as I hope that anyone that actually ends up watching this. So yeah, I don't expect I expect I will make some mistakes. So please, let me know if I get anything wrong, and I'd be happy to, discuss any questions with anyone that has them. So please feel free to leave any questions. And with that, let's get started. So I'm going to go and share my screen. All right. And let's begin with chapter 1, introduction. So 1.1, materials processing, paragraph 1. Chemically reactive plasma discharges are widely used to modify the surface properties of materials. Plasma processing technology is vitally important to several of the largest manufacturing industries in the world. Plasma-based surface processes are indispensable for manufacturing the very large-scale integrated circuits, or ICs, used by the electronics industry. Such processes are also critical for the aerospace, automotive, steel, biomedical, and toxic waste management industries. Materials and surface structures can be fabricated that are not attainable by any other commercial method, and the surface properties of materials can be modified in unique ways. For example, 0.2 micron, 4 micron deep trenches can be etched into silicon film or substrates, as shown in figure 1.1. A human hair is 50 to 100 microns in diameter, so hundreds of these trenches would fit endwise within a human hair. Unique materials such as diamond films and amorphous silicon for solar cells have been produced, and plasma-based hardening of surgically implanted hip joints and machine tools have extended their working lifetime many-fold. So if we look at figure 1.1, we can see a cross-sectional image of one of these, manufactured features, specifically a very deep trench. So this is a silicon substrate where a 0.2 micron by 4 micron deep hole has been, drilled or machined out of it. Okay, let's keep going. It is instructive to look closer to integrated circuit fabrication, which is the key application that we describe in this book. As a very incomplete list of plasma processes, argon or oxygen discharges are used to sputter deposit aluminum, tungsten, or high-temperature superconducting films. Oxygen discharges can be used to grow silicon dioxide films on silicon. Dichlorosilane/ammonia and tetraethyl orthosilicate O2 discharges are used for this plasma-enhanced chemical vapor deposition, PECVD, of silicon nitride and silicon dioxide films, respectively. Boron trifluoride discharges can be used to implant dopant, in this case, boron atoms into silicon. Fluorocarbon, chlorine, oxygen discharges are used to selectively remove silicon films, and oxygen discharges are used to remove photoresist or polymer films. These types of steps, deposit or grow, dope or modify, etch or remove, are repeated again and again in the manufacturing of a modern integrated circuit. They are the equivalent on a micrometer size scale of centimeter size manufacturing using metal and components, bolts and solder, and drill press and lathe. For micro fabrication of an integrated circuit, 1/3 of the tens to hundreds of fabrication steps are typically plasma based. So yeah, in this section, we're kind of introduced to the three main categories of what we're doing with the plasmas. We have a removal process, such as etching, where we can, we remove a layer. We have an additive process where we can grow a layer, so one material on top of another, or we have the process of modifying, which we call doping. So where you take, let's say you start with just silicon and you want to implant boron into it to change the conductivity of the material. So those are our main three things we can do. We can add layers, remove layers, or modify the layers. And again, in a modern chip, to produce a chip layer by layer, you do these steps hundreds to thousands of times, and about 1/3 of those use a plasma in some way, either from cleaning, etching, deposition, so on. So figure 1.2 shows a typical set of steps to create a metal film pattern with submicrometer feature in a large area or 300 millimeter diameter wafer substrate. In A, the film is deposited. In B, a photoresist layer is deposited over the film. In C, the resist is selectively exposed to light through a pattern. This is called photolithography. And in D, the resist is developed, removing the exposed resist regions and leaving behind a pattern resist mask. In E, this pattern is transferred into the film by an etch process. The mask protects the underlying film from being etched. In F, the remaining resist mask is removed. Of these 6 steps, plasma processing is generally used for film deposition and etch, and may also be used for resist development and removal. Yeah, so in this figure here, we're just seeing the processes, kind of a simplified process for making just one layer on a chip. So in order to build a full chip, you would repeat this process, hundreds of times. And again, plasmas are used can be used basically for each of these steps. So the etch process in E is illustrated as leading to vertical sidewalls aligned with the resist mask. That is, the mask pattern has been faithfully transferred into the metal film. This can be accomplished by an etch process that removes material in the vertical direction only. The horizontal etch rate is 0. Such anisotropic etches are easily produced by plasma processing. On the other hand, one might imagine that exposing the masked film to a liquid or vapor phase etchant will lead to undercut or isotropic profiles shown in figure 1.3a, compared to 1.2, which is produced by equal vertical and horizontal etch rates. Many years ago, feature spacings between trenches were tens of micrometers, much exceeding required film thickness. Undercutting was then acceptable. This is no longer true with sub-micrometer feature spacing. The reduction in feature size and spacings makes anisotropic etch processes essential. In fact, strictly vertical etches are sometimes not desired. One wants controlled sidewall angles. Plasma processing is the only commercial technology capable of such control. Anisotropy is a critical process parameter in integrated circuit manufacture and has been a major force in driving the development of plasma processing technology. So here we're introduced to one of our key sort of design goals, and that's how isotropic or anisotropic our feature is. So isotropic just means that the etch is equal in all directions, while anisotropic means that the downward etch is much greater than the lateral etches. And if we look at figure 1.3, we see the difference. Here in A, we see a very isotropic etch where once the etchant comes in, it's going to go the same in all these directions, versus an anisotropic etch is, the etch rate down is much larger than the etch rate to the side. Now, if we look at figure 1.1, we see here this is clearly an anisotropic etch. Okay, continuing. The etch process applied to remove the film in figure 1.2d is shown in figure 1.2e as not removing either the photoresist or the underlying substrate. This selectivity is another critical process parameter for integrated circuit manufacturers. So again, in figure 1.2 here, we have multiple layers of different kinds of materials. So selectivity is our ability to remove just one of those materials and not remove other materials. Some etch chemistries are perfectly selective, meaning they only will react with one material, leaving the other one alone. But a lot of materials are somewhere in between in that there is some characteristic lateral etch rate to the downward etch rate. So whereas wet etches have been developed having essentially infinite selectivity, highly selective plasma etch processes are not easily designed. Selectivity and anisotropy often compete in the design of a plasma etch process, which results, as shown in figure 1.3b. Compare this to the idealized result shown in 1.2e. Assuming that the filmed substrate selectivity is a critical issue, one might imagine simply turning off the plasma after the film has been etched through. This requires good endpoint detection system. Even then, variation in film thickness and etch rates across the area of the wafer imply that the etch cannot be stopped at the right moment everywhere. Hence, depending on the process uniformity, there's a need for some selectivity. These issues are considered further in chapter 15. Okay, so now we're introduced to this other idea, uniformity. So when you're making these wafers, you start with some uniform 300 millimeter wafer, and you're making a bunch of different chips over the course of the wafer. So each of these squares, that I'm drawing here just represents another chip. When you're doing the process, you usually can't get 100% uniformity, meaning that the chips at your edge might get etched differently than the chips in the center. All right, so that's not ideal. Ideally, you would apply the same uniform process over the entire wafer, but this is very difficult to achieve and something that you have to try to work hard to obtain. So just to summarize this, we've kind of been introduced to a couple of our design goals here. So isotropic versus anisotropic, selectivity, and uniformity. So we're going to, over the course of this, learn how to design for each of these things. Going on now, here's a simple recipe for etching silicon using a plasma discharge, starting with an inert molecular gas, such as CF4. Inert meaning that if you just exposed the gas to silicon, nothing would happen. So exciting the discharge to sustain a plasma by electron-neutral dissociative ionization. So here, given by this chemical reaction, the electron hits the CF4, ionizes it, creating 2 electrons. A single ion is now made of CF3+, and then we have just an F by itself. These unbonded, either atoms or molecules, we're going to call radicals, just as a general category. Okay. And to create reactive species by electron-neutral dissociation. So in this case, the electron hits the CF4, does not ionize it, so we conserve the number of electrons as opposed to adding another electron. But we're creating these chemically reactive species of either fluorine or CF3, CF2. Okay. The etchant F atoms react with the silicon substrate to yield the volatile etch product SiF4. And by volatile, we just mean that it wants to be a gas. So once you form it, it will come off the surface into the gas and you can pump it out. So here, S and G indicate solid and gaseous forms, respectively. Finally, the product is pumped away. It is important that CF4 does not react to silicon and that the etch product SiF4 is volatile so that it can be removed. The process etches silicon isotropically. For an anisotropic etch, there must be a high-energy ion CF3+ bombarding the substrate, as illustrated in 1.3c and d. Energetic ions leaving the discharge during the etch bombardment bombard the bottom of the trench but do not bombard the sidewalls, leading to anisotropic etching by one of 2 mechanisms. Either the ion bombardment increases the reaction rate of the surface, or it exposes the surface to the etchant by removing passivating films that cover the surface. So, what we're saying here is if you didn't have any ions, and this is just a chemical process, you would get this isotropic etch. In order to get the anisotropic etch, we need the ions, and these ions can assist by one of 2 ways, either by getting energy to the bottom of the well and increasing the reaction rate at the bottom as compared to the sidewalls. And the reason they move in straight lines is because of their charge, they respond to the electric field that forms. The other mechanism is kind of a little bit more complicated in that there's the addition of a passivating film. So I drew it and I highlighted it in green, but you can place a passivating film on the sidewalls, and at first you would place it on the bottom here, but what happens is the ions come in, remove that passivating film, which opens it up to the chemical reactions to happen at the bottom. So either of these ways can enhance the anisotropic etch. Okay, just continuing on now. Similarly, chlorine and bromine atoms created by dissociation in a discharge are good etchants for silicon, F atoms and CF2 molecules for silicon dioxide, O atoms for photoresist, and chlorine atoms for aluminum. In all cases, a volatile etch product is formed. However, F atoms do not etch aluminum, and there's no known etchant for copper, because the etch products are not volatile at reasonable substrate temperatures. So all this is saying is you have to find the right chemistry to etch each material. So each material that you want to remove is kind of its own, is its own problem. So there's principles that apply to all of them, but the specific chemistries are different. So we see the importance of the basic physics and chemistry topics treated in this book. 1, plasma physics, chapters 2, 4 through 6, and 18 to determine the electron, ion densities, temperatures, and ion bombardment energies and fluxes for a given discharge configuration. And 2, gas phase chemistry. And 3, surface physics and chemistry, chapters 7 and 9, to determine the etch densities and fluxes and the etch rates with and without ion bombardment. The database for these fields of science is provided by 4, atomic and molecular physics, which we discuss in chapter 3 and 8. We also discuss applications of equilibrium thermodynamics, chapter 7, to plasma processing. The measurement and experimental control of plasma and chemical properties in reactive discharges is itself a vast subject. We provide brief introduction to some simple plasma diagnostic techniques throughout the text. And specifically, I want to try and, when we reach these points, and the book doesn't go too much detail, we'll probably detour into some other texts and maybe some research papers that explain some of these different diagnostic techniques. From this entire paragraph, we see that we're combining a lot of different fields of science. We need to understand, plasma physics in order to understand how the plasma is going to respond to electromagnetic radiation that we, apply to the plasma to power it. We also need to understand chemistry and surface chemistry to understand etch rates. Yeah. So overall, it's a very, something that the reason I like this field a lot is that we have to pull together a bunch of different fields to try and understand what's going on. All right, continuing on. We have motivated the study of the fundamental of plasma processing by examining isotropic and anisotropic etches for IC manufacture, integrated circuit manufacture. These are discussed in Chapter 15. Other characteristics motivate its use for deposition and surface modification. For example, essential feature of low-pressure low pressure processing discharges that we consider in this book is that the plasma itself, as well as the plasma substrate system, is not in thermal equilibrium. This enables substrate temperatures to be relatively low compared to those required in conventional thermal processes while maintaining adequate deposition or etch rates. Putting it another way, plasma processing rates are greatly enhanced over thermal processing rates at the same substrate temperature. For example, silicon nitride films can be deposited over aluminum films by PECVD, whereas adequate deposition rates cannot be achieved by conventional chemical vapor deposition, CVD, without melting the aluminum film. Chapter 16 gives further details. So, yeah, this idea that the plasma is not in equilibrium is really important. If a system is in equilibrium, we can describe the entire system with one temperature. But in this case, we're really going to, at least in the discharges we care about, are going to be really comprised kind of two main temperatures. There's the electron temperature, so TE here, and then there's the basically everything else, which is the ion temperature or gas temperature. So in this case, the gas and the ion temperature will be close to equilibrium and will be a little bit above room temperature. They might warm up depending on how much power you put into the plasma, but the electron temperature is going to always be much larger than the ion temperature because the electron temperature can actually respond to the electric fields that we're putting into it and gain energy. So that's going to allow us to generate very interesting chemistries that otherwise could only be generated if you heated up the entire system to very, very high temperatures. Okay, going on. Particles or dust can be a significant component in processing discharges and can be a source of substrate level contamination in etch processes. One can also control dust formation in useful ways. For example, to produce powders of various sizes, or to incorporate nanoparticles during deposition to modify film properties. Dusty plasmas are described in Chapter 17. So a lot of these processes, let's say you have a methane plasma. If you run the methane plasma for long enough, you will slowly generate carbon nanoparticles. And if that's what you want, that's great, but it can also damage deposition. So if you don't want the dust there, it can be a problem. And when we get to this, I'll also go over, there's more and more research showing that you can actually use these small dust particles as diagnostics in your plasma. So you can track, if you can, using basically a fast frame camera, if you can, in a laser sheet, if you can track the movement of the dust in the plasma, you can get some properties of the plasma itself. So there's a lot of interesting stuff there. Okay, continuing. The non-equilibrium nature of plasma processing has been known for many years, as illustrated by the laboratory data in Figure 1.4. In time sequence, this shows first the equilibrium chemical etch rate of silicon in the xenon fluoride etchant gas. Next, the tenfold increase in etch rate with the addition of argon ion bombardment of the substrate, simulating plasma-assisted etching. And finally, the very low etch rate due to physical sputtering of silicon by ion bombardment alone. So that's referencing Figure 1.4 down here, which is a very famous experiment by Coburn and Winters, which shows that it's really the synergy of the chemical process with the ion bombardment that is what's leading to the etch rate. Because in the first part over here, we have just pure chemical etching, which is very, very slow for the xenon difluoride. And on the right, we have pure physical etching. So this is where an argon ion beam is exposed to the substrate is exposed to this argon ion beam. And the argon here comes in, hits the surface, and will eject out. So we call this a physical etching or sputtering. And we can see that both by themselves have very slow etch rates. And when we combine them, it's not simply the sum of those two etch rates. It's they work together to enhance each other. And we get this very large, greater than tenfold increase in etch rate. Okay. A more recent application is the use of plasma immersion ion implantation, or PIII, or I'll just say pi, to implant ions into materials at dose rates that are tens to hundreds of times larger than those achievable with conventional beam-based ion implantation systems. In pi, a series of negative high voltage pulses are applied to a substrate that is immersed directly into a discharge, thus accelerating plasma ions into the substrate. The development of pi has opened a new implantation regime characterized by very high dose rates, even at very low energies, and by the capability to implant very large areas in irregularly shaped substrates, such as flat panel displays or machine tools and dies. This is illustrated in Figure 1.5. Further details are given in Chapter 16. So what's shown here is, on the left is kind of how you would traditionally get ions implanted into the object, where you would expose it to a monodirectional beam coming in. And in order to cover the entire substrate, you'd either have to rotate the substrate or you'd have to rotate the beam. Versus with pi, you stick the entire thing into the plasma. the plasma naturally forms a electric field which uniformly covers the substrate, and then you pulse it with a high negative voltage, which pulls in ions into it. So that's pretty cool. So plasmas. A plasma is a collection of free charged particles moving in random directions that is, on average, electrically neutral. This book deals with weakly ionized plasma discharges, which are plasmas having the following features. 1, they are driven electrically. 2, charged particle collisions with neutral gas molecules are important. 3, there are boundaries at which surface losses are important. 4, ionization of neutrals sustains the plasma in the steady state. And 5, the electrons are not in thermal equilibrium with the ions. Okay, so here we just get our general definition of the plasma. So important here, and he's going to go into it in more detail in a second, but the book deals with weakly ionized plasma discharge. So weakly, meaning that a small percentage are actually ions. So if you start with all neutral gas, only 1% or maybe less than that of the neutral atoms get ionized. That's in opposition to fully ionized plasmas, such as fusion plasmas, where there's essentially no neutral species left. Driven electrically, that means that we will have an electrode that in the case that we're concerned about will primarily drive them with radio frequency voltage oscillations. So that's how we're going to supply power to the system, is by applying AC voltages to it. Section 2, so charged particle collisions with neutral gas molecules are important. So in the case of, let's say, a fusion plasma, there are very, very few collisions between charged particles and neutrals. But in these low density plasmas where, you have low ionization, it's, almost all of the system is still neutral. Those charged particle with neutral collisions are important. 3, there are boundaries at which surface losses are important. So this is kind of obvious, but we won't be the alternative is to be at such high pressure that all of the energy that's lost by collisions happens kind of inside the volume. We're not going to be that high pressure. We're going to be in this somewhat lower pressure regime where energy and particles are lost to the wall. So the walls act as absorbing boundaries to these species. So 4, ionization of neutrals sustains the plasma in steady state. And 5, the electrons are not in thermal equilibrium with the ions. So that last one is really important. So the electron temperature is going to be much greater than the ion temperature. And again, that's in opposition to related, but its own field of study of fusion plasmas, where the ion and electron temperature are often in equilibrium. So, for a simple discharge is shown schematically in figure 1.6b. It consists of a voltage source that drives current through a low pressure gas between 2 parallel conducting plates or electrodes. The gas, quote, breaks down to form a plasma, usually weakly ionized. That is, the plasma density is only a small fraction of the neutral gas density. We describe some qualitative features of plasmas in this section. Discharges are described in the following section. So, plasmas are often called a fourth state of matter. As we know, a solid substrate in thermal equilibrium generally passes into a liquid state as the temperature is increased at a fixed pressure. The liquid passes into a gas as the temperature is further increased. At a sufficiently high temperature, the molecules in the gas decompose to form a gas of atoms that move freely in random directions, except for infrequent collisions between the atoms. If the temperature is further increased, then the atoms decompose into freely moving charged particles, electrons, and positive ions, and the substance enters the plasma state. This state is characterized by common charged particle density. So electron density is approximately the ion density. And in equilibrium, the electron temperature is equal to the ion temperature. The temperatures are required to form plasmas from pure substances in thermal equilibrium range from roughly 4,000 Kelvin to easy to ionize elements like cesium to 20,000 Kelvin for hard to ionize elements like helium. The fractional ionization of the plasma is given by this equation here. Now, again, this is the case of an equilibrium plasma. So if you wanted to take a gas, let's say helium, you did not want to use electric fields to generate the plasma. You instead just wanted to use temperature to create the plasma. You would have to raise the temperature to up to 20,000 Kelvin. Now, in the case of the plasmas that we're interested in this book and for plasma processing, we don't want to have to raise it to that temperature. We're trying to avoid that huge temperature raise. So we'll use electric fields to drive the plasma, and these electric fields allow us to create a non-equilibrium plasma where the electron temperature is larger than the ion temperature. Okay, just finishing out this, where density of the gas is the neutral gas density, XIZ is near unity for fully ionized plasmas, and XIZ is much less than 1 for weakly ionized plasmas. Much of the matter in the universe is in the plasma state. This is true because stars, as well as most interstellar medium, are plasmas. Although stars are plasmas in thermal equilibrium, the light and heavily charged particles in low pressure processing discharges are almost never in thermal equilibrium, either between themselves or with the surroundings. Because these discharges are electrically driven and are weakly ionized, the applied power preferentially heats the mobile electrons, while the heavy ions efficiently exchange energy by collisions with the background gas. Hence, TE is much larger for TI for these plasmas. All right. Figure 1.7 identifies kinds of plasmas on a log N versus log TE diagram. There's an enormous range of densities and temperatures for both laboratory and space plasmas. Two important types of processing discharges are indicated on the figure. Low pressure discharges are characterized by an electron temperature of 1 to 10 volts and an ion temperature much less than the electron temperature, and densities between e to the 8, e to the 13 centimeters cubed. These discharges are used to minimize these discharges are used as miniature chemical factories in which feedstock gases are broken into positive ions and chemically reactive etchants, which I'll call radicals throughout the book. So deposition precursors and so on, which then flow to and physically or chemically react at the substrate surface. While energy is delivered to the substrate also, for example, in the form of bombarding ions, the energy flux is there to promote the chemistry in the substrate and not to heat the substrate. The gas pressure for these discharges are low, between 1 millitorr and 1 torr. These discharges and their use for processing are the principal subject of this book. We give the quantitative framework for their analysis in chapter 10. I'm going to finish these paragraphs and then we'll look at the diagram and talk a little bit about that. So high pressure discharges are also used for processing. These discharges have electron temperature between 0.1 and 2 volts and densities between 10 to the power 14 to 19 centimeters cubed. And the light and heavy particles are more nearly in thermal equilibrium, with the temperature of the ions less than or approximate to the electron temperature. These discharges are used mainly to deliver heat to the substrate, for example, to increase surface reaction rates, to melt, sinter, or evaporate materials, or to weld or cut refractory metals. Operating pressure are typically near atmospheric pressure, 760 torr. High pressure discharges of this type are beyond the scope of this book. Figure 1.8 shows the densities and temperatures or average energies for various species in a typical RF-driven capacitively coupled low-pressure discharge. For example, for silicon etching using CF4, as described in section 1.1, we see that the feedstock gas, etchant atoms, etch product gas, and plasma ions have roughly the same temperature, which do not exceed a few times room temperature, 0.026 volts. And as a rule of thumb, it's 1/40th of an electron volt. Okay. The etchant F and product SiF4 densities are significant fractions of the CF4 density, but the fractional ionization is very low, e to the -5. The electron temperature is 2 orders of magnitude larger than the ion temperature. However, we note that the energy of the ions bombarding the substrate can be 100 to 1,000 volts, much exceeding TE. The acceleration of the low temperature ions across a thin sheath region where the plasma and substrate meet is central to all processing discharges. We describe this qualitatively below and quantitatively in later chapters. So we'll talk about that in a second, but let's discuss these figures a bit. So the book is really focusing on this low pressure discharges. Okay. So again, they're not super high temperature. They're non-equilibrium. They're low ionization fraction and so on. So furthermore, kind of in this corner over here are fusion experiments, which are both high temperature and higher density, with a fusion reactor being, kind of up here. Now, just as a quick note, fusion reactors do have, when he's kind of putting fusion reactors up in this, high density, high temperature region on the plot, that's talking about the core of a fusion reactor. So fusion reactors, if we just draw the shape of a fusion plasma, so here's the core of the plasma. Fusion plasmas will generally have a region called the diverter. That is, so up here, the core is this kind of high temperature, high density where fusion reactions are occurring. But this region down here will actually be a lot more similar to these discharges. So for those that are kind of interested in this sub-problem of the diverter region, a lot of the information in this book is directly applicable to this. So then again, stuff like solar wind is, very much so, very low density, but can be quite high in temperature. So yeah, and then finally, just as kind of terrestrial plasma, so Earth's ionosphere flames fall into these very low temperature, kind of medium density discharges. So yeah, okay. All right, and then in figure 1.8, again, just these are kind of showing the differences in the temperatures of these different species. So the electron temperature is much higher than the ions. However, this is describing the plasma ions and electrons in the bulk of the plasma. So more detail will follow in this chapter on this. But if we think of the plasma kind of existing here, and then we have our boundary of our, let's say, plasma reactor here. So this is just our wall. When we're talking about the plasma and electron temperatures, we're talking about the plasma that's kind of in the center of our box here. And in that case, they're not in equilibrium, so the electron temperature is much larger than the ion temperature. However, there's a region that will form, and we'll discuss in much more detail in a second, but there's a region that will form near the wall called the sheath, which is a strong electric field that forms that will increase the energy of the ions. So the ions have a very low energy when they're inside the bulk of the plasma, but after they pass through the sheath, they actually gain a lot more energy than the electrons. And then finally, just as far as density goes, the actual gas itself is the most dominant species. Then after that, you have the etch product that's being formed, as well as the free radicals. But those are all much larger than how much actual ion and electrons. So the neutrals, the density of the neutrals is much more than the density of the electrons for our plasma. In the case, like I said, in the case of a fusion plasma, this is the opposite's true, that there's essentially no neutrals left once you get to high enough ionization. Okay, let's keep going. All right, so I think we started off here. So although Ni and Ne may be 5 orders of magnitude lower than the gas density, the charged particles play central roles in sustaining the discharge and in processing. Because electron temperature is larger than ion temperature, it is the electrons that dissociate the feedstock gas to create the free radicals, etchant atoms, and deposition precursors required for the chemistry of the substrate. Electrons also ionize the gas to create the positive ions that subsequently bombard the surface. As we have seen, energetic ion bombardment can increase chemical reaction rates at the surface, clear inhibitor films from the surface, and physically sputter materials from or implant ions into the surface. So all this is saying is, even though there's not that many electrons or ions, they still play in these discharge plasmas. They still play, a fundamental role in both generating the species, as in the case of the electrons, as well as delivering energy to the surface in the case of the ions reaching, passing the sheath and reaching the surface. Okay, continuing. TE is generally less than the threshold energies for dissociation and for ionization of the feedstock gas molecules. Nevertheless, dissociation and ionization occur because the electrons have a distribution of energies. So letting G epsilon d epsilon be the number of electron per unit volume with energies lying between epsilon and epsilon plus d epsilon, then the distribution function is sketched in figure 1.9. So electrons having energies above the dissociation or ionization cannot dissociate or ionize the gas. We see that dissociation and ionization are produced by the high energy tail of the distribution. Although the distribution is sketched in the figure, as it were, Maxwellian in the bulk electron temperature TE, this may not be the case. The tail distribution might be depressed below or enhanced above a Maxwellian by electron heating and electron-neutral collision processes. Two temperature distributions are sometimes observed with the electron temperature for the bulk electrons lower than TH for the energetic electron tail, or TH being the hot electrons. Non-Maxwellian distributions can only be described using the kinetic theory of discharges, which we introduced in chapter 18. So what is this saying? So if I have, let's say I have some dimer molecule here with some bond, it requires a certain amount of energy, this E dissociation, in order to break the bond into two single, now chemical radicals. So there's some threshold energy for each of these processes. And then there's a threshold energy for ionization, meaning, an electron hits the ion and then it spits out 2 electrons and 1 ion. Okay. So there's threshold energies for this, and dissociation is usually less than the ionization threshold. But the temperature, which let's say this is 2.5 volts, this is, 5 volts. The electron temperature will be less than that. Let's say this is 1 volt, just to put some numbers to it. But the thing to remember is when we say that the electrons have some temperature, what that's really saying is they have a distribution around some mean. Okay, so some population of the electrons it's a small amount, but it's not insignificant. Amount of the electrons are above these thresholds, and a lot of engineering goes into trying to get this tail region to be how you want it. So the kind of key takeaway is that this high energy tail of the electron distribution is what's actually driving your chemistry. And it can be suppressed if you have too many collisions. Let's say your background pressure is too high, you can actually suppress your tail. But then depending on how you do your radio frequency heating, there's all sorts of tricks to try to manipulate the shape of this tail, let's say to enhance the tail, okay, to where it extends out longer. And that means if the tail is longer, that means a higher fraction of the electrons have the sufficient energy to carry out these reactions. All right, so let's discuss the plasma sheath now. So plasmas, which are quasi-neutral, meaning that the electron density is approximately equal to the ion density, are joined to wall surfaces across thin positively charged layers called sheaths. To see why, first note that the electron thermal velocity is at least 100 times the ion thermal velocity because the mass is much smaller. So electrons are much smaller, so they move, and they're at a higher temperature, so they move much, much faster than the ions. Okay, consider a plasma of width L with electron density equal to ion density initially confined between two grounded absorbing walls, shown in figure 1.10a. So let's just look at that real quickly. So here's our our setup here. And this is we're going to start with the grounded walls and then a uniform density across length L for the electrons and ions. Okay. Because the net charge density is 0, the electric potential phi, and the electric field E is 0 everywhere. Hence, the fast-moving electrons are not confined and will rapidly be lost to the walls on a very short time scale. However, some electrons near the walls are lost, leading to the situation shown in figure 1.10b. So a thin positive ion sheaths form near each wall in which the ion density is larger than the electron density. The net positive rho within the sheath leads to the potential profile phi of x, which is positive within the plasma and falls sharply to 0 near both walls. This acts as a confining potential valley for electrons and a hill for ions because the electric fields within the sheaths point from the plasma to the wall. Thus, the force acting on electrons is directed into the plasma. This reflects electrons traveling towards the walls back into the plasma. Conversely, ions from the plasma that enter the sheath are accelerated into the walls. With the plasma potential with respect to the walls, then we expect that the plasma potential is approximately a few times larger than the electron temperature in order to confine most of the electrons. The energy of the ions bombarding the walls is then a few TE. Charge uncovering is treated quantitatively in Chapter 2 and sheaths in Chapter 6. So just to summarize that, if we were to start in this situation where you had perfectly uniform equal electron and ion density, what would happen very quickly is all the electrons would move out to the wall and it would create a charge imbalance that generates a potential. And this potential acts to both confine the electrons in the center as well as accelerate the ions outwards. So anywhere that you have these, either a grounded or a floating wall, you'll develop the sheath around it, which is really important because, like we said earlier, the sheath acts to give a bunch of energy to the ions and basically accelerates them, and it can accelerate it higher than the electron temperature. Figure 1.11 shows sheath formation as obtained from a particle and cell plasma simulation. We use particle and cell results throughout the book to illustrate various discharge phenomena. In this simulation, the left wall is grounded, the right wall is floating, and the positive ion density is uniform and constant in time. The electrons are modeled as in sheets having charge to mass ratio minus E over M that move in one dimension along X under the action of the time-varying fields produced by all the other sheets, the fixed ion charge density, and the charges on the walls. The electrons do not collide with other electrons, ions, or neutrals in the simulation. 4,000 sheets were used with electron temperature of 1 volt, and the ion density shown there, at time t equals 0. In A, B, C, and D, we respectively see the Vx electron phase space, electron density, electron field, and potential after the sheath is formed at time 0.77 microseconds. Okay, so what do we see here? Basically, here we have our phase space, so our velocity versus our position. So it's uniformly spread, and then there's a spread in velocity because there's some temperature, right? So this is 1 voltage spread in velocity, and then we have a nice, spread spatially in X that's uniform. And what we see here, I'll read this out, what it says, but this system will naturally organize if the ions are kept stable, and we can keep it stable because the time scales are so different. The electrons are moving much, much faster. So in respect to the electrons, the ions are essentially static, but the electrons some of them will naturally get lost to the wall, which will then create a charge imbalance in the sheath region. So if we just we can segment out this plot to show this is the region of the sheath. And because there's a charge imbalance, you develop an electric field. All right. And this electric field acts to, again, to confine the electrons in the middle and accelerate the ions to the wall. Now, I'll continue reading here. So 40 sheets have been lost to the wall to form the sheaths. Figure 1.180 shows the absence of electrons near each wall over sheath width, which is approximately 6 millimeters. Except for fluctuations due to the finite number, the point of the plasma to the walls, Ex is negative at the left wall and positive at the right wall to repel plasma electrons. The potential in the center of the discharge is approximately 2.5 volts. In the fall to zero to the left wall, this wall is grounded by definition. The potential at the right wall is also low, but we see that in figure F that it oscillates in time. We will see that chapter 4 that these are plasma oscillations. So we'll go in more detail, like he says, in future, but the plasma is always characterized by some fundamental plasma frequency. So this is the speed that, I guess, the frequency that the electrons will kind of wiggle back and forth inside the plasma. And it's a very important sort of way to characterize a plasma. So if the ions are also modeled as moving objects, then on longer timescales, we would see ion acceleration within the sheaths and a consequent drop in ion density near the walls as sketched in figure 1.2b. We return to this in chapter 6. The separation of discharges into bulk plasma and sheath regions is an important paradigm that applies to all discharges. The bulk region is quasi-neutral, and both instantaneous and time-averaged fields are low. The bulk plasma dynamics are described by diffusive ion loss and high pressure and free fall ion loss at low pressures. In the positive space charge sheaths, high fields exists, leading to dynamics that are described by various ion space charge sheath laws, including low voltage sheaths and various high voltage sheath models, such as collisions and collisional child laws and their modifications. The plasma and sheath dynamics must be joined at their interfaces, as we will see in chapter 6. The usual joining condition is to require the mean ion velocity at the plasma sheath edge to be equal to the ion sound speed, called the Bohm velocity, where E and M are the charge and mass of the ion respectively, and TE is the electron temperature in volts. So what we're describing here, and this is going to be kind of constant throughout the book, is we usually will split the plasma into two regions. If I just draw a box here, again, we will have some sort of core quasi-neutral plasma where the electron density and the ion density are the same, and that there are no electric fields that are sustained because they're able to the electrons and the ions are able to cancel each other out. And then there will be some region near the walls where this quasi-neutrality is broken. So if I were to just plot, let's see here, if we plot X and we plot, let's see, density inside the plasma, the electron density is equal to the ion density. Then at some point, kind of as we progress towards the wall, the electron density is going to drop much faster than the ion density is towards the wall. And again, this difference in the electron density and ion density generates the potential, the voltage drop across the sheet that gives energy to the ions. And then we need to usually join the two at some point. So there's some boundary conditions that we're going to have to apply between the bulk plasma and the sheath. Okay, so let's move on to section 1.3, discharges. So far we've been talking about kind of some of the physics and chemistry behind the generating these plasmas, but now we're going to transition a little bit more to the technological side. So radio frequency diodes. Capacitively driven radio frequency discharges, so-called RF diodes, are commonly used for materials processing. An idealized discharge in plane parallel geometry, shown in figure 1.12a, consists of a vacuum chamber containing two planar electrodes separated by a spacing L and driven by an RF power supply. The substrates are placed on one electrode, feedstock gases are emitted to flow through the discharge, and effluent gases are removed by the vacuum pump. Coaxial discharge geometries, such as the hexode, shown in figure 1.12b, are also in widespread use. Typical parameters are shown in table 1.1. The typical RF-driven voltage is between 100 and 1,000 volts, and the plate separation is between 2 to 10 centimeters. When operated at low pressure, with the wafer mounted on the powered electrode and used to remove substrate materials such as reactors, are commonly called reactive ion etchers. A misnomer, since the etching is a chemical process enhanced by energetic ion bombardment of the substrate, rather than a removal process due to reactive ions alone. Okay, so if we look here, this is just kind of your simplest RF discharge geometry that you have. So you have your RF source that's 100 to 1,000 volts, and it's usually at 13.56 megahertz frequency. And your substrate, so in the case of semiconductor manufacturing, your 300 millimeter wafer is placed on one of the electrodes, and then the plasma is generated in the middle, and you have two sheaths that form on either side. And something I want to definitely get into later in this series is going into some of the vacuum tech needed to do this. But this would be, you would pump this entire chamber out to pump it out to be a vacuum, and then re-add in your pure feedstock gases, which are then decomposed by the plasma, and then you need to pump them back out. And then a top view is given below here. So for anisotropic etches, typically pressures are in the 10 to 100 millitorr power densities and 0.1 to 1 watt per centimeter square. The driving frequency is 13.56 megahertz, and multiple wafer systems are common. Typical plasma densities are relatively low, between 10 to the 19, 10 to the 11 centimeters cubed. And the electron temperature is the order of 3 volts. Ion acceleration energies or sheath voltages are higher, greater than 200 volts, and fractional ionization is low. The degree of dissociation of the molecules into reactive species is seldom measured, but can range widely from less than 0.1% to nearly 100%, depending on the gas composition and plasma conditions. So the reactive species or the radicals are seldom measured, and we're definitely going to go into why that is in the future. It's just difficult to measure, but we'll talk about what diagnostics you can use to do that, and how much, what dissociation fraction you have can vary widely depending on how much power you're putting into the system. For deposition and isotropic etch applications, pressures tend to be higher, ion bombarding energies are lower, and the frequencies can be lower than the commonly used standard 13.56 megahertz. So the operation of capacity-driven discharge is reasonably well understood, as shown in figure 1.13 for a symmetrically driven discharge. The mobile plasma electrons responding to the instantaneous electric field produced by the RF driving voltage oscillate back and forth within the positive space charge cloud of the ions. The massive ions respond only to the time averaged electric fields. Oscillations on the electric cloud generate sheath regions near each electrode that contain net positive charge when averaged over an oscillation period. That is, the positive charge exceeds the negative charge in the system, with the excess appearing within the sheaths. So just as a quick pause there, the ions, again, because they're cold, they only see the average field. So in the bulk of the plasma, where it's quasi-neutral, the average field is 0, but the average field in the sheaths is, you do have a non-zero potential in the sheath region, so the ions do get accelerated by that. The electrons, however, will oscillate and respond quickly to the RF field that's being formed, the field that's being formed by the RF radio frequency generator. Okay, this excess produces a strong time average electric field within each sheath directed from the plasma to the electrode. Ions flowing out of the bulk plasma near the center of the discharge can be accelerated by the sheath fields to high energies as they flow to the substrate, leading to energetic ion-enhanced systems. Typical bombarding energies can be as high as the RF voltage. Now remember, when we say the RF voltage, the RF is a alternating field, so usually we're either referencing the kind of like peak to zero field or the peak to peak field, or maybe there's an average. Maybe you're referencing the average field. So just keep that in mind when we're talking about the RF voltage. So typical ion bombarding energies can be as high as the RF voltage divided by 2 for a symmetric system, and as high as the RF at the powered electrode for the asymmetric system. A quantitative description of capacitive discharges is given in chapter 11. And then here we see the table gives us some standard pressures for these as the text described, and then we get a little bit more of a detailed, in this case, density profiles of what's going on inside of the sheath. And this is asymmetric, as you can see. So the sheath B is a little bit smaller than the sheath A. In the middle here, we still have the electron cloud, where inside the middle, you do have the ion density and electron density canceling out. But once you get inside the sheaths, again, you have the electron density drop and the ion densities experience the electric field. Yeah, okay. Continuing. We note that the positive ions continuously bombard the electrode over an RF cycle. In contrast, electrons are lost to the electrode only when the oscillating cloud closely approaches the electrode. During that time, the instantaneous sheet potential collapses to near zero, allowing sufficient electrons to escape the balance. The ion charge delivered to the electrode. Except for such brief moments, the instantaneous potential of the discharge must always be positive with respect to any large electrode and wall surface. Otherwise, the mobile electrons would quickly leak out. Electron confinement is ensured by the presence of a positive space charge sheath near all the surfaces. We will see that the critical limiting factor of RF diodes is that the ion bombarding flux, given by this expression here, and the bombarding energy cannot be varied independently. So what that's saying is if you want more electrons, you have to supply a larger RF voltage, okay? Which this is going to lead to higher ion energy that reaches the substrates. So you can't vary those independently, and that's kind of that's one of the reasons why this capacitively coupled discharge is not always ideal, in that if you want to up the electron density, you're going to start having to increase the ion energy as well, which can damage your substrate. This situation is analogous to the lack of independent voltage and current control in diode vacuum tubes or semiconductor PN junctions. For a reasonable but relatively low ion flux, as well as a reasonable dissociation of the feedstock gas, sheath voltages at the driven electrode are high. For wafers placed on the driven electrode, this can result in undesirable undesirable damage or loss in line with control. Furthermore, the combination of low ion flux and high ion energy leads to a relatively narrow process window for many applications. The low process rates resulting from limited ion flux in RF diodes often mandates a multi-wafer or batch processing with consequent loss of wafer-to-wafer reproducibility. Higher ion and neutral fluxes are generally required for single wafer processing in a clustered tool environment, in which a single wafer is moved by a robot through a series of process chambers. Clustered tools are used to control interface quality and are said to have the potential for significant cost saving in fabricating ICs. Finally, low fractional ionization poses a significant problem for processes where feedstock gas and disposal of effluents are issues. So again, the fact that we can't uncouple electron density and the energy of the ions means that you have a limited process window. So in an ideal world, you can control those independently, and that's going to motivate the subsequent plasma types that we will discuss. All right, continuing. To meet the alignment, selectivity, and damage control demands for next generation fabrication, the mean ion bombarding energy and its energy distribution should be controlled independently of the ion and neutral fluxes. Some control over ion bombarding energy can be achieved by putting the wafer on an undriven electrode and independently biasing the electrode with a second RF source. Although these so-called RF triode systems are in use, processing rates are still low at low pressures, and sputtering contamination is an issue. Another approach is dual frequency operation, in which a high and low frequency RF source are used to drive one or both of the plates in an RF diode. The high frequency mainly controls the ion flux, and the low frequency controls the ion bombarding energy. Using a frequency higher than the conventional frequency of 13.56 MHz for the low frequency drive results in an increased ion flux at the substrate for a fixed power input and allows for the low frequency drive to better control the ion energy. High frequencies of 27.1, 60, or 160 MHz and low frequencies of 2 or 13.56 MHz are used commercially. So the idea here is to use a separate RF supply to drive your substrate that has the wafer to kind of shield out some of those high energy ions, but it's still limited. Various magnetically enhanced RF diodes and triodes have also been developed to improve performance of the RF reactor. These include, for example, magnetically enhanced reactive ion etchers, in which direct current magnetic fields of 50 to 300 Gauss is applied parallel to the powered electrode in which the wafer sits. The magnetic field increases the efficiency of power transfer from the source of the plasma and also enhances plasma confinement. So if you think of if a magnetic field is pointing this way, so that's my B field, and then I have electrons, the electrons will want to circle around the magnetic field. So applying the magnetic field can help with confinement by kind of keeping the electrons bottled in, but it can also help by giving alternative mechanisms for getting the RF waves to impart energy on the electrons. So that'll be kind of the subject of plasma waves as we go forward. This result is a reduced sheath voltage and an increased plasma density when the magnetic field is applied. However, the plasma generates a strong non-uniform both radially and azimuthally. To decrease process uniformity, at least azimuthally, the magnetic field is slowly rotated in the plane of the wafer, for example, at a frequency of half a hertz. While this is an improvement, these systems may not have good uniformity, which may limit their applicability to next generation submicron devices and fabrication. So if we think about let's just say, for example, we have a wafer right here, and we want to use one of these magnetically enhanced. Let's say I have some coils that are generating, we're driving current azimuthally to create a magnetic field going inwards. The magnetic field is always going to have some kind of curvature to it like this. And because the magnetic field itself is not symmetric, it's going to lead to a non-uniform plasma, which, like we said earlier, uniformity is a major, goal of our process. So high density sources. So the limitations of RF diodes and their magnetically enhanced variants have led to the development of a new generation of low pressure, high density plasma sources. A few examples are shown schematically in figure 1.14, and typical source and plasma parameters are given in table 1.1. A quantitative description is given in chapters 12 and 13. In addition to high density and low pressure, a common feature is that the RF or microwave power is coupled to the plasma across a dielectric window, so meaning a glass window. Rather than by direct connection to an electrode in the plasma, as for an RF diode, this non-capacitive power transfer is the key to achieving a low voltage across all plasma sheaths at electrode and wall surfaces. Direct current voltages and hence ion accelerations are typically 20 to 30 volts at all surfaces. To control the ion energy, the electrode on which the wafer is placed can be independently driven by a capacitively coupled RF source. Hence, the independent control of the ion radical fluxes through the source power and the ion bombarding energy through the wafer electrode power is achieved. Okay, so what this is saying, and it will show a schematic next, but instead of having two plates that there's an electric field that generates between, this is the capacitive coupling, we're instead going to use some sort of either wave heating or inductive coupling. So if we imagine, I guess, how should I put this? Instead of capacitively coupling, we could create an inductor antenna. So this is just our inductor. We have put positive, negative here, and we have our nice little, voltage, RF voltage driving this. The plasma, basically you couple inductively. So the plasma acts as a winding, just like you would have with a transformer. And this allows you to put power in without directly increasing the ion energy. So in the next page, we'll have some more pictures. The common feature of power transfer across dielectric window and separate bias at the wafer electrode are illustrated in figure 1.1. However, sources differ significantly in the means by which power is coupled in the plasma. For the electron cyclotron resonance source shown in figure 1.14a, one or more electromagnetic coils surrounding the cylindrical source chamber generate an axially varying DC magnetic field. Microwave power is injected axially through a dielectric window into the source plasma, where it excites a right-handed, circularly polarized wave that propagates to a resonance zone for a cold electron, where omega is the cyclotron frequency, where the wave is absorbed. Here, omega is 2 pi times the frequency. If the applied radiant frequency, which is given by this expression, is the electron gyration frequency at resonance for the typical microwave frequency used, F is equal to 2,450 megahertz, and the resonant magnetic field is around 875 Gauss. The plasma streams out of the source into the process chamber in which the wafer is located. So if we just look at that really quickly, this is given by this top left configuration here. So again, we have coils which are generating a magnetic field, and then microwaves are pushed into the system, and the microwave frequency has to resonate with the frequency of the, so if I draw like a one field line of the magnetic field, the electron is going to circle around the magnetic field at some frequency, which is given by the expression down here, the EB over M. So if we put in a RF frequency that is at the same frequency as the electron rotating around the field line, we can push power into the plasma. So again, you can already see that this is quite a bit more complicated. You now have microwave RF source. You have to have an externally applied field, and you're going to have challenges with uniformity with this. Alternatively, very similar, but kind of a bit beyond me, is if you do alternatively to a ECRH source, is you can use different shaped coils to excite different types of resonances with the plasma. That's kind of my level of understanding. So these being something like helicon waves, and then in the case here we have a helicon resonator. So each of these is a little bit, they are similar. The difference is in the detail of what type of plasma wave you're propagating. So we'll go into more detail, and I'll learn that hopefully in a little bit more detail in the future. Alternatively, quite simply, with no need of an external magnetic field, is simply just an inductively coupled plasma. So again, you have a simple coil, this is just what I drew in the last page. You have a simple coil that you connect this to your RF generator here, and it inductively couples. So it's going to generate a magnetic field like this, and then the plasma acts like it couples as if the plasma was a single wound transformer. So again, this is kind of the most commonly used inductively coupled plasma, just because it doesn't require any of these additional external magnetic fields. Okay, So I'll continue reading. A helicon source, as shown in figure 1.14b. Okay, continuing on now. A helicon source is shown in figure 1.14b. A weak 50 to 200 Gauss DC axial magnetic field together with an RF-driven antenna placed around the dielectric cylinder that forms the source chamber allows excitation of a helicon wave within the source plasma. Resonant wave-particle interaction is believed to transfer the wave energy to the plasma. For the helical resonator shown in figure 1.14c, the external helix and the conducting cylinder surrounding the dielectric discharge chamber form a slow wave structure, that is, supporting the electromagnetic wave with a phase velocity much less than the velocity of light. Efficient coupling of the RF power to the plasma is achieved by excitation of a resonant axial mode. An inductive or transformer coupled source is shown in 1.14d, where the plasma acts as a single-turn lossy conductor that is coupled to a multi-turn non-resonant RF coil across the dielectric discharge chamber. RF power is inductively coupled to the plasma by transformer action. In contrast to ECR and helicon source, a DC magnetic field is not required for efficient power coupling in helical resonator or inductive sources. So again, the goal of these is what's nice about these bottom two is they do not need the magnetic field. Now, something that was mentioned earlier, but I'll just reiterate, is now that your RF source is coupled inductively, so your plasma is coupled inductively up here, you can attach this to a different either RF or just a DC voltage source to basically screen out ions that you don't want. So you can put this to, you can basically bias this to whatever you want to get the energy that you want. So you can put it to a positive voltage to screen out ions, or you can put it at a negative voltage to pull ions in and give yourself some more energy. All right. Figure 1.14 also illustrates the use of high-density sources to feed plasma into a relatively distinct, separate process chamber in which the wafer is located. As shown in the figure, the process chamber can be surrounded by DC multipole magnet fields to enhance plasma confinement near the process chamber surfaces while providing a magnetic, near field-free plasma environment at the wafer. So again, we're sort of separating the plasma generation region from the processing region. Such configurations are often called remote sources, a misnomer since at low pressure considerable plasma and free radical production, remember free radicals is just the chemically reactive species, occurs within the process chamber near the wafer. Sometimes the source and process chambers are more integral. For example, the wafer is placed very near the source exit to obtain increased ion and radical fluxes, reduce spread in ion energy, and improve process uniformity. But the wafer is then exposed to high levels of damaging radiation. So point is even if these are sometimes called remote sources, that remoteness is really dependent on how close you place the wafer to this kind of like exit region here. Okay. Although the need for low pressure, high fluxes, and controllable ion energy has motivated high density source development, there are many issues that need to be resolved. A critical issue is achieving the required process uniformity over 300 millimeter wafer diameters. In contrast to the nearly one-dimensional geometry of typical RF diodes, high-density cylindrical sources can have length to diameter ratios order or exceeding unity. Basically, the systems are more complicated and larger. For the plasma formation and transport in such geometries is inherently radially non-uniform. Another critical issue is efficient power transfer across dielectric windows over a wide operating range of plasma parameters. Degradation of and the deposition of the window can also lead to irreproducible source behavior and the need for frequent costly cleaning cycles. Low pressure operation leads to severe pumping requirements for high pressure or etching rates and hence the need for large, expensive vacuum pumps. Furthermore, plasma and radical concentration becomes strongly sensitive to reactor surface conditions, leading to the problem of reactor aging and process irreproducibility. Finally, DC magnetic fields are required for some source concepts. These can lead to magnetic field-induced process non-uniformities damage, as seen, for example, in the MIRI systems. So to summarize, you can achieve higher densities and this sort of this independent control of your density and your ion energy, but it's at the cost of complexity of the system, both just in the number of parts, but also the complexity of it not being radially symmetric anymore. And if you're going to use these systems, that requires a lot more design and a lot more, modeling and simulation to get it right. Figure 1.15 illustrates schematically the central problem of discharge analysis using the example of an RF diode. Given the control parameters of the power source, so frequency, driving voltage, or absorbed power, the feedstock gas, pressure, flow rate, and chemical composition, and the geometry, simplified here to the discharge length L, then find the plasma parameters, including the plasma density, the etchant density, the ion and etchant fluxes, hitting the substrate, the electron, ion temperature, the ion bombarding energy, and the sheath thickness. The control parameters are the knobs that can be turned in order to tune the properties of the discharge. The tuning range for a given discharge is generally limited. Sometimes one type of discharge will not do the job no matter how it is tuned, so another type must be selected. As suggested in Figure 1.2 and 1.14, a bewildering variety of discharges are used for processing. Some are driven by RF, some by DC, and some by microwave power sources. Some use magnetic fields to increase the plasma confinement or the efficiency of the power absorption. One purpose of this book is to guide the reader toward making wise choices when designing discharges used for processing. So all that is to say is the process space for plasmas is very large. We have a lot of different types of plasma sources, and we have a lot of different conditions which we would like to achieve. And not every plasma source can achieve every condition. So the more we understand the process and can get a feel for which, type of plasma is appropriate for which type of process you're doing, the more you'll be able to, pick the right source, so to speak. Okay. So now we'll just go on to this final section real quickly on symbols and units. The choice of symbols is always vexing. While the various fields each have their consistent set of symbols to represent physical quantities, these overlap between different fields. For example, plasma physics and gas phase chemistry. For example, H is standard for enthalpy in chemistry, but is also standard for magnetic field in plasma physics. This also occurs within a given field. For example, K is standard for Boltzmann's constant, but also for wave number. When there's always the occasional symbol that must be stand-in for many things in different contexts. We sometimes distinguish these by using different lettering. Roman, italic, script, boldface, for example, I is the current and I is a modified Bessel function. M is the ion mass and M is the number of chemical species. We can often distinguish commonly used symbols by the use of subscripts. For example, sigma denotes the cross-section, but the sigma RF and sigma DC denote electrical conductivities. We've done this whenever the notation is not too cumbersome. Meaning should be clear from the context in most cases. To help avoid confusion, we have provided a table of symbols and abbreviations in the front matter of this book. These give the normal usage of the symbols and their units. As far as possible, we use the SI system of units, meters, kilograms, seconds, and coulombs for charge. In these units, the charge on an electron is minus E. The unit of energy is a joule. We often use the symbol epsilon for the voltage that is the equivalent of the energy. That is, in joules, it would be E times epsilon, where epsilon is in volts. I'll just make a note here. Whenever I say electron volts, I mean the energy. And the electron volt is just defined as the energy gained by an electron if it passes a voltage drop of 1 volt. Okay. We also occasionally use the calorie, which is 4.187 joules. The SI unit of pressure is the Pascal, but we more commonly give gas pressure in torr. And I think the reason, if you are familiar with, if you're American and you use vacuum systems, you'll use torr for all of your pressure measurements. We occasionally use the atmosphere, which is 760 torr and equal to 1 bar. But to refer to gas pressure, the SI unit of magnetic field is Tesla, but we more often use Gauss. We use the symbol T to refer to temperature in kelvins. The energy equivalent temperature in joules is KT, where K is, I'll let you read it. We often use the Roman typeface symbol T for the voltage equivalent of the temperature, where E times T is equal to K times T. Hence, room temperature is 297 Kelvin. I'll usually round it up to 300 Kelvin. And that's equivalent to 0.026 volts or 1/40th of an electron volt. Even within the standard unit system, quantities are often designated by subunits. For example, cross-sections are often given in centimeters squared rather than meters squared in tables, and wavelengths at microwave frequencies are commonly given in centimeters rather than meters. To assist our readers in making calculations, we give the commonly used constants in the SI units of units system. We give the commonly used constants in the SI system of units and the most common conversion between units in the front matter of the book. It is sometimes tempting to make a calculation in non-standard units. For example, the collision frequency, which has units of meters cubed, meters squared, meters per second, could equally well be calculated in commonly used centimeters, since the length units cancel. However, we urge the student not to make such shortcuts, but to systematically convert to standard units before making calculations. And that's what I will do. I found it's just always better to convert everything into standard units, then do the calculation, and then convert back if needed. So now I'll take just a second to review a couple kind of key things. So from, what are we trying to do? We're trying to with these plasmas, we're trying to either etch, deposit, or dope. And remember, doping is just modifying. And when we want to talk about, our ability to do this, or kind of how would we describe the quality of these processes, a couple of things come to mind. And specifically, things we really care about is anisotropic versus isotropic etching. We care about the selectivity of our process. So when we want to remove a layer, we want to just remove that specific material, not the other ones. And then we really care about uniformity of our process. Because again, when we're doing these plasma discharges, we're trying to make chips on a wafer, and we would like every chip to come out the same. So if our plasma process is highly non-uniform, it's very difficult to do this. So yeah, so we want those. Some of our process, properties of the plasma that we have that we want to try to choose are the pressure of the plasma, the electron temperature, the voltage that the ions have. We want to control the fluxes of our ions to the surface, the fluxes of the neutrals. And then, of course, we have control over, what is our species fraction, so fraction of species I, what gases are we feeding in? And to achieve these different, plasma conditions, we have different technologies. So we have capacitively coupled discharge, we have inductively coupled discharges, and then we have our various wave, think ECR discharges, helicon discharges, for example. So we have kind of different, of course, we can also just have a DC plasma. So we have different technologies to try to achieve different process conditions, to achieve like our different etch depositions and doping. And then finally, like I said earlier, what's fun about this is we need to understand a decent bit of electromagnetics. We need to understand some atomic and molecular physics, and we need to understand chemistry. And I'll add in as well, we need to understand fluid mechanics when it comes to designing our pumping systems, because we have to pump a bunch of gas in and out of our reactors. So, okay. With that, thank you for listening if you made it this far, and I'll see you for the next chapter.